Hello everyone. I'm going to discuss quality assurance and implementation, and this is the 16th chapter of the book Systems Analysis and Design by Kendall and Kendall. For our learning objectives, at the end of this chapter, you will be able to recognize the importance of users and analysts taking a total quality approach to improve the quality of software design and maintenance. Then you'll realize the importance of documentation, testing, maintenance, and auditing. You will be able to understand how service-oriented architecture and cloud computing is changing the nature of information system design. You will be able to design appropriate training programs for users of the new system. You'll be able to recognize the differences among physical conversion strategies and be able to recommend an appropriate one to a client. And then you'll address security, disaster preparedness, and disaster recovery concerns for traditional and web-based systems. Finally, you'll be able to understand the importance of evaluating the new system and be able to recommend a suitable evaluation technique to a client. So the topics that we're going to discuss are the following. We'll discuss Six Sigma, quality assurance, walkthroughs, structured charts, modules, documentation, testing, and then we'll discuss about client-server computing, the different network types, groupware, training, security, organizational metaphors, and finally, we'll have some evaluation. Alright, so we'll begin by discussing total quality management. And total management quality is very important throughout the system's development steps. The concept of quality has broadened over the years to reflect an organization, and quality is now an evolutionary process. That means quality is constantly innovating and upgrading, and it gears toward perfection. That is referred to as what we call now the total quality management. And systems analysts must be aware of the factors that are driving the interest in quality. And it's very important to realize that the increasing commitment of businesses to total quality management fits well into the overall objectives of systems analysis and design. So to begin with our discussion, we'll discuss about Six Sigma. So Six Sigma has changed the approach to quality management. Systems analysts and systems users need to be aware of Six Sigma and apply some of the principles to their systems analyst projects. It was originally developed by Motorola in the 1980s, and Six Sigma is more than a methodology. Actually, it's a culture built on quality. The goal of Six Sigma is to eliminate all defects, and this applies to any product. It also applies to service or process. In operations management textbooks from the 1970s to the end of the century, we will see that quality control was built in or was expressed in terms of three standard deviations from the mean, or 3 sigma. So we call it 3 sigma, which is equals about 67,000 defects per million opportunities. So Six Sigma implies a goal of no more than 3.4 defects per million opportunities. So actually that's the origin of Six Sigma. Now, to discuss more about Six Sigma, it uses a top-down approach. So what is the meaning of top-down approach? So most probably it requires a CEO or Chief Executive Officer to adopt the philosophy, and as executive to serve as the project champion. A Six Sigma project leader is called a black belt. So the metaphor of the black belt comes from the ranking system of capabilities in martial arts, right? And black belts are certified after they have successfully led projects. Other members or other project members are called green belts. All right? And master black belts are black belts who have worked on many projects and are available as resource to project teams. Six Sigma can be summarized as a methodology, and the steps of Sigma or Six Sigma are shown in this figure. Okay, you can see from here that Six Sigma is much more than a methodology. It's actually a philosophy and a culture. Alright, so if you want to know more about Six Sigma, you can visit the website for the Duran Center at the Carlson School of Management, University of Minnesota, in www.csom.umn.edu. So from here you will see the different methodologies that are described in the Six Sigma. Number one is to define the problem, and then number two is to observe the problem. Number three is to analyze the causes of the problem, and then number four is to act on the causes. Number five is to study the results, and six, standardize the changes, and finally draw conclusions. Practically speaking, a large portion of the responsibility for the quality of information system rests with systems, users, and management. And there are two things that should happen for total quality management to become a reality with systems projects. First, the full organizational support of management must exist, which is a departure from merely endorsing the newest management gimmick. So such support means establishing a context for management people to consider seriously how the quality of information systems and information itself affects their network. Second, early commitment to quality from the analyst and business users is very important to achieve the goal of quality. And this commitment results in exerting an evenly paced effort toward quality throughout the system's development life cycle. And it stands in stark contrast to having to pour huge amount of effort into ironing out problems at the end of the project. One of the strongest quality management actions that the systems analyst team can take is to do structured walkthroughs routinely. Structured walkthroughs are a way of using peer reviews or reviewers so that they can monitor the system's programming and overall development. They can also point out problems, and they can also allow the programmer or analyst which is responsible for that portion of the system to make suitable changes. So basically, structured walkthroughs involve at least 4 people. The first one is the person responsible for the part of the system or subsystem being reviewed. It can be a programmer or an analyst. Second, a walkthrough coordinator. Third, a programmer or analyst, peer. And finally, a peer who takes notes about the suggestions. So each person attending a walkthrough has a special role to play. So basically, the coordinator is there to ensure that the others adhere to any roles assigned to them and to ensure that any activities scheduled are accomplished. So the function of the programmer or analyst is there to listen and not to defend his or her thinking or rationalize a problem or argue. Now, the programmer or analyst is to present and then point out errors or potential problems. And they are not there to specify how the problem should be remedied. And lastly, the note taker records what is said so that the others present can interact without encumbrance. Now, many companies first introduced computer systems on the lowest level of the organization, and this is where the immediate benefits to computerizations are most observable and cost effective. Businesses often take this approach to systems development by going out and acquiring, for example, commercially off-the-shelf software for accounting, or another for marketing, for example. So when in-house programming is done with a bottom-up approach, it's difficult to interface. So basically, the problem with the bottom-up approach is that it is sometimes difficult to interface the subsystem so that they can perform smoothly as a system. Thus, the top-down design was used to replace the early approach, and the top-down design allows the systems analyst to ascertain overall organizational objectives and how they are best met in an overall system. Okay, so the analyst, what the analyst does is to divide the system into subsystems and their requirements. So basically, that's the top-down approach, from the top going down. The advantages of using a top-down approach to systems design include avoiding the chaos of attempting to design a system all at once. So as we have seen, planning and implementing management information systems is very complex, and attempting to get all subsystems in place and running at once is agreeing to fail. A second advantage of taking a top-down approach is that to design, it enables separate systems analysis teams to work in parallel on different but necessary subsystem, and this can save a great deal of time because the use of teams for subsystems design is particularly well suited to a total quality assurance approach. The third advantage is that the top-down approach avoids a major problem associated with a bottom-up approach. No, it prevents systems analysts from getting so mired in detail that they lose sight of what the system is supposed to do. So total quality management and the top-down approach to design can go hand in hand. And the top-down approach provides the systems group with a ready-made division of users into task forces. These are the specialized teams of users for the subsystems, and task forces set up in this manner can serve a dual function. They can serve as quality circles for the management information system. The necessary structure for quality assurance is in place, as in proper motivation for getting the subsystem to accomplish the departmental goals that are important to the users involved. Once the top-down design approach is taken, The modular approach is useful in programming, and this approach involves breaking the programming into logical, manageable portions or modules. And this kind of programming works well with the top-down design because it emphasizes the interfaces between modules and does not neglect until later in systems development. Ideally, each individual module should be functionally cohesive, accomplishing only one function. Modular program design has three main advantages. First, modules are easier to write and debug because they are virtually self-contained. And then tracing an error in a module is less complicated because a problem in one module should not cause problems in others. The second advantage of modular design is that modules are easier to maintain. That means modifications usually will be limited to a few modules and will not be spread over an entire program. A third advantage of modular design is that modules are easier to grasp because they are self-contained subsystems. Hence, a reader can pick up a code listing of a module and understand its function. Some guidelines for modular programming include the following. Number one, keep each module to a manageable size. So ideally, including only one function is an ideal size. Number two, pay particular attention to the critical interfaces, which means the data and control variables that are passed to other modules. Number three, minimize the number of modules that user must modify when making changes. And finally, maintain the hierarchical relationships set up in the top-down phases. The recommended tool for designing a modular top-down system is called a structure chart. Alright? And a structure chart is simply a diagram consisting of rectangular boxes representing the modules and connecting lines. The hollow circle arrows represent the data being passed up and down the structure, and filled in circle arrow represents a control switch or flag. So we can see from the illustration the definition of the following, no? So this is an example of a structure chart which encourages top-down design using modules. So the rectangular boxes represents the modules, and then you'll see some arrows. All right, and in this figure, as you can see, a set of modules is used to change a customer record, and it shows 7 modules, no? 1, 2, 3, 4, 5, 6, 7, and they are labeled 000, 100, 110, 120, and so on. Okay, this numbering allows programmers to insert modules using a number between the adjacent module numbers. For example, a module inserted between 110 and 120 would receive the number 115. Now, on the sides of the connecting lines, 2 types of arrows are drawn. So you can see the 2 types of arrows. The arrows with the empty circles are called data couples. Okay? And the arrows with the filled-in circles are called control flags or switches. So a switch is the same as a control flag, except that it's limited to 2 values, either yes or no. And these arrows indicate that something is passed. Alright? It's either down to the lower module or up to the upper one. And ideally, the analyst should keep this coupling to a minimum. The fewer data couples and control flags one has in the system, the easier it is to change the system. And when these modules are actually programmed, it's important to pass the least number of data couples between the modules. Alright? And even more important is the numerous control flags should be avoided. So control is designed to be passed from the lower level modules to those higher in the structure. And on rare occasions, it will be necessary to pass control downward in the structure. When the control is passed downward, a low-level module is allowed to make a decision. And the result is a module that performs two different tasks. And this result violates the ideal of a functional module. It should perform only one task. Now, even when a structure chart accomplishes all the purposes for which it was drawn, the structure chart cannot stand alone as the sole design and documentation technique. Why? First, it doesn't show the order in which the modules should be executed. What will accomplish that? A data flow diagram will accomplish that. Second, it doesn't show enough detail, and a structured English technique or method will accomplish that. Alright? Modular development has led to a concept called service-oriented architecture, or SOA. But that is very different from the modules in the structure chart. Instead of being hierarchical, like the top-down approach found in structure charts, the SOA approach is to make individual SOA services that are unassociated or only loosely coupled to one another. So definitely, in the service-oriented architecture, each service executes one action, and each service can be used in other applications within the organization or even in other organizations. So we can say that service-oriented architecture is simply a group of services that can be called upon to provide specific functions rather than including calls to other services. A service can be used or use certain defined protocols so that it can communicate with other services. Now, the burden of connecting services in a useful fashion is also a typical process, and it's called orchestration, and it's placed upon the system's designer. And this can be accomplished by selecting services from a menu of services and monitoring them by setting up an service-oriented architecture dashboard. Okay? But in order to set up a SOA, services must be, number one, modular. It should be reusable, work together with other modules, or we call it the interoperability, able to categorize and identify, and able to be monitored. Finally, it should comply with industry-specific standards. The total quality assurance requires that programs should be documented properly, and software systems and formal and informal procedures need to be documented so that systems can be maintained and improved. Documentation also allows the users, the programmers and analysts to see the system. They can see the software and procedures without having to interact with it. And as we have learned, the turnover of information service personnel has been high in comparison with other departments. So chances are that the people who conceive, for example, the original system will not be the same as the one who is maintaining it in the present time. Okay? So, well-updated documentation will shorten the number of hours required for new people to learn the system before performing the maintenance. And there are many reasons why systems and programs are undocumented or underdocumented. And some of the problems reside with the systems and programs themselves. Others with systems analysts and programmers. So basically, systems analysts, sometimes they fail to document systems properly because they don't have the time, or they are not rewarded for the time spent documenting. And some analysts do not document because they dread doing so or think it's not their real work. Okay? But some analysts are reticent about documenting the systems, especially if the systems are not their own. They fear that if they include incorrect material about the someone else's system, for example, they might be in trouble. So defenders of the SDLC's approach, or the Systems Development Life Cycle approach, remind us that documentation is accomplished by means of a case tool, a computer-aided software engineering tool. And it's done during the analysis phases, which addresses many of the problems. In system documentation, we have what we call procedural or procedure manuals. And procedure manuals are common organizational documents that most people have seen. They are the English language component of the documentation, although they may also contain program codes, flowcharts, and so on. Manuals are intended to communicate to those who use them, and they may contain background comments, steps required to accomplish different transactions, instructions on how to recover from problems, and what to do next if something is not working, or we call it the troubleshooting. Many manuals are now available online with hypertext capability that facilitates use. Okay? A straightforward, standardized approach to creating user support documentation is also desirable. And to be useful, user documentation must be kept up to date. And the use of the web has revolutionized the speed with which assistance can be obtained by users. Nowadays, many software developers has revolutionized the space of helping people through creating user support, such as manuals, frequently asked questions pages. They also set up online chats and user communities to the World Wide Web. And the Folklore Method mentioned here is a system documentation technique, and it was created to supplement some of the techniques just covered. In the event, or even the plethora of techniques are available, many systems are not adequately documented, or sometimes they are not documented at all. Folklore gatherers are information that is often shared among the users, but it's very seldom to write it down. The Folklore Method was first developed in the 1980s, okay, before the creation of blogs and user communities. And it has advantages, like for example, folklore is structured and it results in more organized and more complete documentation. Second, the Folklore Method encourages someone familiar with the software to seek out information rather than depending on users to come forth on their own. Alright? So we can see from here the definition of the two system documentation. So the procedural manuals are the English language component. So some of the The key sections of the procedural manuals are the following. So they can have an introduction, how to use the software, what to do if things go wrong. It can contain a technical reference section, also an index and an information on how to contact the manufacturer. Furthermore, procedural manuals complaints, for example, some of the complaints for procedural manuals are the following. Sometimes some manuals are poorly organized, and sometimes they are hard to find. It's really hard to find the needed information in a particular manual because they are poorly designed and organized. So some of the complaints are also like this. The specific case in question does not appear in the manual. Okay, so basically it's about the organization of the manual itself. And then the manual sometimes is not written in plain English. So sometimes they are written in a very highly technical terms. Okay, for the folklore, so basically the folklore methods collects information in categories such as customs, tales, sayings, and art forms. Alright, so from here you will see the illustration, okay, of the customs, tales, sayings, and art forms used in the folklore method of documentation, which apply to information systems. Okay, so the objective of this illustration is to gather information corresponding to one of 4 categories, no, such as customs, sayings, art forms, and tales. No, for the sayings, for example, do this and it works, or do this and it works. And for the customs, descriptions of how the users currently get the system to run. In the art forms, it contains diagrams, tables, and flowcharts. And the tales, these are the stories about how the users were able to get the system to work, even if it's not, for example, the proper way to make the system work. Now, the techniques discussed in this chapter are valuable as design tools. They can be a memory aid. They can be used for productivity tools and as a means of reducing dependencies on key staff members. And the systems analyst, however, can face difficult decisions regarding which method to adopt. So how do we choose a design and documentation technique? So the following is a set of guidelines to help the analyst use the appropriate technique. So basically, the analyst should choose a technique that is it compatible with the existing documentation? Is it understood by others in the organization? Number 3, does it allow you to return to working on the system after you have been away from it for a period of time? 4th, is it suitable for the size of the system you are working on? 5th, does it allow for a structured design approach if that is considered to be more important than other factors? And finally, you choose a technique that does allow for easy modification. Now, once the analyst has designed and coded the system, testing, maintenance, and auditing of it are prime considerations. Okay? So we'll try to deal with these things one by one. So let's begin with the testing process. Now, the system's newly written or modified application programs, for example, okay, including the procedural manuals, new hardware, and the different system interfaces, they all should be tested thoroughly. Alright? So testing is done throughout the system's development and not just at the end. No? That's the typical problem with many systems developers. They only test at the end of the development stage. But actually, it should be done throughout the system's development. Okay? So it's meant, the testing process is meant to turn up unknown problems and not to demonstrate the perfection of programs, manuals, or equipment. Alright? Although testing is tedious, it's an essential series of steps that helps ensure the quality of the system. And it's far less disruptive to test than to have a poorly tested system that will fail after the installation, right? So testing is accomplished on subsystems or program as work progresses. It can be tested on program modules. So testing is done on many different levels at various intervals. And before the system is put into production, all programs must be checked. Okay, so we can test the program by testing. Okay, so we call it program testing with the test data. Okay, so we check the program with test data and check to see if the modules work together with one another as planned. Okay, next, the system as a working whole must also be tested. So it includes the different interfaces between subsystems. So from there, we consider testing the different links with test data. Okay, so that includes as I have said, we test the interfaces between subsystems, and we also test the correctness of the output and the usefulness and understandability of systems documentation and output. We can also have full system testing with the test data, and then right after that we can have full system testing with the live data. Alright, so shown in the figure below, as you can see, the programmers, analysts, what else? Operators, and the users, they all play different roles in the various aspects of testing. So this is shown here. Okay, so testing of hardware, for example, is typically provided as a service by vendors of equipment, and they will run their own tests on equipment when it's delivered on site. Okay, so basically these are the things that connects the different people that are involved in various testing phases. Okay, the responsibility for program resting resides with the original authors of each program, and the systems analyst serves as an advisor and coordinator for program testing. And in this capacity, the analyst works to ensure that correct testing techniques are implemented by programmers, but probably does not personally carry out this level of checking. And at this stage, okay, programmers must first check, or must first desk check their programs to verify the way the system will work. And in desk checking, the programmer follows each step in the program on paper to check whether the routine works as it is written. Next, programmers must create both valid and invalid test data. So these data are run to see if base routines work and also to catch errors. So if output from the main modules is satisfactory, you can add more test data so as to check the other modules. Created test data should test possible minimum and maximum values, as well as all possible variations in format and codes. File output from the test data must be carefully verified. It should never be assumed that data contained in a file are correct just because a file was created and accessed. And throughout this process, the systems analyst checks output for errors. No? So you can see from here, advising the programmer of any needed corrections. And the analyst will usually not recommend or create test data for program testing, but might point out to the programmer omissions of data types to be added in later tests. Alright? Next is the link testing with the test data. So when programs pass desk checking and checking with the test data, they must go through the link testing. And this is referred to as the string testing. Alright? Link testing checks to see if the programs that are independently actually work together as planned. Okay? So the analyst creates special test data that cover a variety of processing situations for link testing. First, typical test data are processed to see if the system can handle normal transactions. So basically, those that would make up the bulk of its load. Now, if the system works with normal transactions, variations are added, including those with invalid data. Okay? To ensure that the system can properly detect errors. So that's how we do testing. Okay? Next, the full system testing with the test data. So when link tests are satisfactorily concluded, the system as a completely entity must be tested. And at this stage, operators and end users become actively involved in testing. So the test data created by the systems analysts for the express purpose of testing system objectives are used. And as can be expected, there are a number of factors to consider when systems testing with test data. Alright? Some of the considerations are the following. For example, they need to examine whether operators have adequate documentation in procedure manuals. Okay? It could be hard copy or online to afford corrections and efficient operations. Number 2, checking whether the procedure manuals, of course, are clear enough in communicating how data should be prepared for the input. Okay? Making sure that the workflows actually really flow, no? So do workflows actually flow? And then determining if the output is correct, and do users understand this output. So basically, the users understand that this is the output, and it should look in its final form. Alright? Finally, we have what we call the testing with the live data. So when system tests using test data prove satisfactory, it's a good idea to try new system with several passes on what is called the live data. So this data are the data that have been successfully processed through the existing system. And this step allows to accurately compare the new system's output with what you know to be correctly processed output, as well as a good idea for testing how actual data can be handled. So obviously, this step is not possible when creating entirely new outputs. Okay? For instance, output from an e-commerce transaction from a new corporate website. So with the test data, only small amounts of live data are used in this kind of system testing. Now, the objective of a systems analyst should be to install or modify the systems that have a reasonably useful life. Now, so as the system analyst, you may want to create a system whose design is comprehensive and far-sighted enough to serve current and projected user needs for several years to come. And part of your expertise should be used to project what those needs might be, and then build flexibility and adaptability into the systems. Okay? And then the better the system design, the easier it will be to maintain, and the less money the business will have to spend on maintenance. Alright? So basically, reducing the maintenance cost when it comes to maintenance practices should be a major concern. Why? Because software maintenance alone can go upward of the 50% of the total processing budget for a business. Alright? And excessive maintenance cost reflect directly back on the system's designer, because approximately 70% of software errors have been attributed to inappropriate software design. And from a systems perspective, it makes sense that detecting and correcting software design errors early is less costly than letting the errors remain unnoticed until maintenance is necessary. So basically, maintenance is performed to improve the existing software rather than to respond to a crisis or system failure. And maintenance are done to update the software, okay, in response to the changing organization. So basically, this work is not as substantial as enhancing the software, but it must be done. Emergency and adaptive maintenance comprises less than half of all system maintenance. And part of the systems analyst job is to ensure that there are adequate channels and procedures in place to permit feedback about subsequent response to maintenance needs. Alright? Users must be able to communicate problems and suggestions easily to those who will be maintaining the system. Solutions are to provide users email access to technical support, as well as to allow them to download product updates or patches from the web. Next thing is the auditing. Auditing is another way of ensuring the quality of the information contained in the system. So auditing is actually broadly defined, but actually auditing refers to having an expert who is not involved in setting up or using the system, and that expert will have to examine the information in order to ascertain its reliability. So whether or not information is found to be reliable, the finding on its reliability is communicated to others for the purpose of making the system's information more useful to them. So there are internal and external auditors, and internal auditors function is to study the controls used in the information system. Alright? They make sure that they are adequate and that they are doing what they are supposed to be doing. And the internal auditors also test the adequacy of security controls. Alright? And they work for the same organization, and they do not report to the people responsible for the system they are auditing. So basically, the work of internal auditors is often more in-depth than that of the external auditors. Why? Because external auditors are used when the information system processes data that influences a company's financial statements. So basically, they audit the system to ensure the fairness of the financial statements being produced. And they may also be brought in there, okay? For example, if there are suspicions of computer fraud or embezzlement of funds. Alright? Now, if the reliability of telecommunications network is very high, it's possible to have what we call a distributed system for businesses, and a setup that can be conceived of as an application of telecommunications. The concept of distributed systems is used in many different ways, and here we will take a broad sense so that it includes workstations that can communicate with each other and data processors, as well as we'll try to understand different hierarchical architectural configurations of data processors that communicate with each other and that have differing data storage capabilities. And in this model, right, the processing functions are delegated either to clients, so the clients can be the users, or to servers, depending on which machines are most suitable for executing the work. And in this type of architecture, the client portion of a network application will run on the client system, and with the server part of the application running on the file server. So basically, with a client-server model, the users interact with limited parts of the application, including the user interface, data input, database queries, and report generation. Alright? But controlling the user access to centralized databases, retrieving or processing data, and other functions, they are all handled by the server. Okay? Now, let's discuss about client-server technology. The client-server model, as we all know, basically, we call it sometimes the client-server computing. Okay? And this model is also called the client-server technology. Sometimes they are also called the client-server architecture. They all refer basically to a design or a design model that can be thought of as an applications running on a network. So basically, that is the meaning of that client-server technology. So in very basic terms, you can picture the client requesting and the server is executing or in some way fulfilling the request. So that would be considered a two-tier client-server architecture. The client-server model has its own advantages and disadvantages. For example, an advantage of the client-server model is that it has greater computer power and greater opportunity to customize applications. While the disadvantage is that it's more expensive, and applications must be written as two separate software components, each running on a separate machines. Alright? So from the illustration here, this is an illustration of a three-tiered client-server configuration. So you can see from the figure, it shows a three-tiered client-server model. And in this figure, you will see the client computers. Okay, they are here. Okay, in the lower left, these client computers access three different tiers of the servers. They access the web server, which handle the web-based exchange of information. They also access the application servers, which process the data to and from the client computers, and finally the database server, which stores and receives the data. So the computers on the network are programmed to perform work efficiently by dividing up processing tasks among the clients and among the servers. So when you think of the client-server model, you think of a system that accentuates the users as the center of the work, and with their interaction with data being the key concept. Although there are two elements working, the client and the server, okay, the intention of the client-server model that users view it as one system. Indeed, the hope is that users are unaware of how the client-server network is performing its distributed processing, okay? Because it should have the look and feel of a unified system. In a peer-to-peer network, PCs can act as either the server of the client, depending on the requirements of the application. Now, the most rapidly growing type of computing nowadays is what we call the cloud computing. And cloud computing has been described as the metaphor for the internet, since the internet is often drawn as a cloud in network diagrams. So basically, using cloud computing, organizations and individual users can use web services, they can use data services or database services, and application services over the internet. So this is done without having to invest in corporate or personal hardware, software, or software tools. Alright? So from the figure below, you will see an illustration that depicts the exchanges between the client computers and services in the cloud. So the illustration of the cloud represents the internet. Okay? So businesses they use web browsers, okay, such as Microsoft Internet Explorer or Mozilla Firefox, Microsoft Edge, Chrome, to access applications. So as you can see, servers store software and data for the businesses. And many large, well-established hardware, software, and consulting companies such as Cisco, Dell, IBM, HP, Microsoft, SAP, and others, they are creating a massive cloud computing endeavors, often with what are termed virtualized resources. What is distinct about these approaches is their ability to grow and adapt to changing business needs. And that is, they are scalable to suit growing or changing demand by the users. So the model of software as a service, also called SaaS, is included in the concept of cloud computing. Now, because networking has become so important, the systems designer needs to consider network design. So whether a systems designer get involved with decisions about the configurations of networks, or whether he or she worries about hardware such as routers and bridges that must be in place when networks meet, the systems designer must always consider the logical design of networks. And an analyst should adapt a set of symbols. For example, in the following diagrams, you'll see a set of symbols to model the network. And it's very useful to have distinct symbols to distinguish. For example, you can distinguish among what are the hubs, what are the external networks, and what are the workstations. So the first step is to draw Okay, a network. Okay, you can draw a network decomposition diagram for illustrating multiple networks and workstation. Okay, you can provide also an overview of the system by drawing a network decomposition diagram. Also, you can draw a hub connectivity diagram. And finally, you can explode your diagram by illustrating hub connectivity to show the various workstations and how they are connected. So, again, these are the symbols when using drawing network decompositions. However, we use different symbols in other systems. Like Cisco, they have different symbols, and in other drawing utilities or tools, they have they can use other symbols. But this is one of the simplest form of symbols that we can use as a systems analyst in a systems analysis design course. Okay? So basically, from here, we can illustrate drawing a network. We can use it to draw a network model. Okay? And so basically, we can start it by, for example, drawing a circle on the top and labeling it. For example, in this example, we have the world's trend network. Okay? So from here, we can see that these circles represents hubs for the marketing division, for the US division, for the other divisions, the Canadian division and the Mexican division. And they extend the drawing by drawing another level. Like for example, in this one, the other level such as it can be workstations on its local area network. For example, in the marketing division, they are divided into subdivisions such as advertising manager and catalog publications, for example. Right? Here we have other divisions of the Mexican division, such as the Mexican warehouse, order entry manager, and order entry clerks. For the Canadian, we have these divisions, and for the US, we have these following divisions. Okay, so basically, that's a very simple network. No? The network is simplified for the purpose of providing a readily understandable example. Okay? So that's an example. Now, we can also make use of a hub connectivity diagram like in this image. And it's very useful for showing how the major hubs are connected. So, for example, in our world's trend network, okay, we have the following connections. No, there are 4 major hubs: the Canadian division, US division, marketing division, and Mexican division. And in addition, there are also some external hubs indicated here. Okay, included are the suppliers. No, they represent the suppliers, and they are needed to be included in the network diagram. Okay, so you can notice that each of the 3 countries are connected to these 21 suppliers. And the marketing division, however, doesn't need to be connected to the suppliers. Only these 3 divisions are connected to the suppliers. So that is how this hub connectivity diagram for world's trend example was given. Okay? Now, another representation here is how we can explode, all right, the hub connectivity diagram into a workstation connectivity diagram. So the purpose of network modeling is to show the connectivity of workstations in some detail. And to do so, we try to explode the hub connectivity diagram. Okay? So here we can see each of the 33 workstations for the US divisions and how they are to be connected. So we can draw the diagrams for this level by examining the third level of the network decomposition diagram. Okay? So we group the items such as the following, like the order entry manager and then the order entry clerks together. Okay? And then we use a special symbol to show multiple workstations and indicate in parentheses. Okay? We indicate in the parentheses the number of similar workstations. In our example, there are 30 order entry clerks. So on the perimeter of the diagram, you can place workstations and they are to be connected to other hubs. And in this way, it will be easier to represent these connections using arrows. Okay, you can also draw the external connections in different color, or you can use thicker arrows. Alright? So this is an example of a workstation connectivity diagram for the example given. Systems analysts engage in an educational process with users, and that is called training. And throughout the system's development life cycle, the user has been involved so that by now, the analyst should possess an accurate assessment of the users who must be trained. Now, in the implementation of large projects, the analysts will often be managing the training rather than be personally involved in it. Alright? So one of the most prized assets that the analyst can bring to any training situation is the ability to see the system from users' viewpoint. And the analyst must never forget what it's like to face a new system. And those recollections can help analysts empathize with users and facilitate their training. Now, training strategies are determined by who is being trained and who will train them. So the analysts will want to ensure that anyone whose work is affected by the new information system is properly trained by the appropriate trainer. For example, whom to train. Okay? All people who will have primary or secondary use of the system must be trained. So they include everyone from the data entry personnel to those who will use output to make decisions without personally using a computer. And the amount of training a system depends on how much someone's job will change because of the new interactions required by the revised system. So you must ensure that users of different skill levels and job interests are separated. And it's certain trouble to include novices in the same training sessions as experts, because novices are quickly lost and experts are rapidly bored with basics. So both groups are then lost. Next are the people who train the users. For very large projects, many different trainers may be used depending on how many users must be trained and who they are. Possible training sources include the following. So they can be the vendors, systems analysts, external paid trainers, in-house trainers, or other system users. And this list gives just a few of the options the analyst has in planning for and providing the training. Alright? Now, what are the objectives of the training? What will be the objective? So basically, the analyst has 4 major guidelines for setting up the training. So they are, number 1, establish the measurable objectives. And number 2, using appropriate training methods. Number 3, selecting the suitable training sites. And number 4, employing understandable training materials. In the training objectives, who is being trained in large part that dictates the training objectives. So training objectives for each group must be spelled out clearly, and well-defined objectives are of enormous help in letting trainees know what is expected of them. And in addition, objectives allow evaluation of training when it's complete. For example, operators must know such basics as turning on the machine, what to do when common errors happen. So they also be trained in basic troubleshooting and how to end an entry. Now, for the training methods, each user and operator will need slightly different training. To some extent, their jobs determine what they need to know, and their personalities, experience, and backgrounds determine how they learn the best. Some users learn best by seeing, right? Others by hearing, and still others by doing. So because it's impossible, or often it's not possible to customize training for an individual, a combination of methods is often the best way to proceed. So that way, most users are reached through one method or another. Methods for those who learn best by seeing include demonstrations of equipment and exposure to training manuals. And those who learn best by hearing will benefit from lectures about procedures, discussions, and question and answer sessions among trainers and trainees. Those who learn best by doing hands-on experience with new equipment, for jobs such as the computer operator, hands-on experience is essential. Whereas a quality assurance manager for a production line may only need to see the output and learn how to interpret it and know when it's scheduled to arrive. For the training sites, basically, it should take place in many different locations, some of which are more conducive to learning than others. Large computer vendors provide special off-site locations. Okay? And sometimes there are operable equipment which are maintained free of charge. And their trainers offer hands-on experience as well as seminars. For example, for settings that allow the users to concentrate on learning the new system. And one of the disadvantages of off-site training is that users are away from the organizational context in which they must eventually perform. Right? Now, there are also on-site training in the user's organization, and it's also possible with several different kinds of training or trainers. The advantage is that users see the equipment placed as it will be in its fully operational in the organizational context. However, there are also disadvantages. For example, the trainees will often feel guilty about not fulfilling their regular job duties if they remain on-site for training. So definitely, full concentration on training may not be possible. Finally, for the training materials, in planning for the training for the users, the systems analyst must realize the importance of well-prepared training materials. And these materials include training manuals, alright? And what else? It needs training cases in which users are assigned to work through a case that incorporates most of the commonly encountered interactions with the system. And also, they also need prototypes and mock-ups of the output. So basically, users of Larger systems will sometimes be able to train on elaborate web-based simulations or software that is identical to what is being written or purchased. Alright? Now, a third approach to implementation is physically converting the old information system to the new or the modified version. And there are many conversion strategies available to analysts, and also a contingency approach that takes into account several users and organizational variables in deciding which conversion strategy to use. So there is no single best way to proceed with conversion actually. However, the importance of adequate planning and scheduling of conversion with the strategic involvement of users, file backup, and adequate security cannot be overemphasized. For conversion strategies, there are 5 strategies for converting from the old system to the new, and they are the following: the direct changeover, parallel conversion, gradual or phase conversion, modular prototype conversion, and the distributed conversion. Conversion by direct changeover means that on a specified date, users stop using the old system and the new system is put into use. The direct changeover can only be successful if extensive testing is done beforehand. And it works best when some delays in processing can be tolerated. Now, direct changeover is considered a risky approach to conversion. Why? Because disruption to the work environment may occur if users resent being forced into using an unfamiliar system without recourse. Finally, there's no adequate way to compare new results with the old. For parallel conversion, it refers to running the old system and the new system at the same time. So they are run in parallel. And when the same results can be gained over time, the new system is put into use and the old one is stopped. One advantage of running both systems in parallel is the possibility of checking new data against the old data. So by this way, we can catch any errors in processing in the new. The main disadvantages include the cost of running 2 systems at the same time and the burden on the employees, okay, of virtually, for example, that their workloads will be doubled during conversion. The third one is the gradual conversion, gradual or phased conversion, which attempts to combine the best features of the 2 previously mentioned plans, and this is without incurring all the risks. And in this plan, the volume of the transactions handled by the new system is gradually increased as the system is phased in. Okay? The advantages of this approach include allowing users to get involved with the system gradually. And it also has the possibility of detecting and recovering from errors without a lot of downtime, as well as the ability to add features one by one. So agile methodologies are sometimes used in this conversion approach. Next, we have the modular conversion. So this conversion uses the building of self-contained operational subsystems to change from the old system to new in gradual manner. So as each module is modified and accepted, all right, it's put into use. One advantage is that each module is thoroughly tested before being used. Another advantage is that users are familiar with each module as it becomes operational. Okay? Their feedback has helped determine the final attributes of the system. And object-oriented approach or methodologies are often used in this particular approach. Okay? Next is the distributed conversion. So this conversion refers to a situation in which many installations of the same systems are contemplated, as is the case in banking or in franchises such as restaurants or clothing stores. One entire conversion is done with any of the four approaches which are considered previously at one site. Alright? And when the conversion is successfully completed, okay, other conversions are done for the other site. Okay? An advantage of distributed conversion is that problems can be detected and they can be contained rather than inflicted simultaneously on all sites. A disadvantage is that even when one conversion is successful, each site will have its own people and culture, along with regional and local people who work through, and they must be handled accordingly. Alright? There are also other conversion considerations, and this conversion entails the details from the analyst, and it includes the following. No? For example, also considered for the conversions are ordering equipments. So basically, it includes the equipment ordering information. And then ordering of any necessary materials. It can be external materials that are supplied to the information system. For example, such as printers, papers, toners, magnetic media, external drives, etc. Next is to appoint a manager to supervise or personally supervising the preparation of the installation site. Alright? Next is the planning, scheduling, and supervising programmers and data entry personnel. So for many implementations, the chief role of an analyst would be to estimate the time needed for each activity. So the analyst will appoint people to manage each sub-project and coordinate their work. For small projects, the analyst will do much of the conversion work on their own. Okay? And many of the project management techniques, such as, for example, Gantt charts, PERT, function point analysis, and successfully communicating with team members are useful for planning and controlling implementation. Alright? Now, we should all be aware of organizational metaphors when we try to implement a system that have just been developed. Alright? Our research, okay, suggested that the success or failure of a system may be related to the metaphors used by an organizational members. So for example, when people in the organization, okay, describe the company as a zoo, okay, like in this figure, you will see from this figure the organizational metaphors that this illustration provides contributions to the success and failure of an information system. Alright? For example, in a traditional MIS, No? If the view of the people, if they describe the company as a war jungle, no, definitely the metaphor of it is that there should, if it is a war jungle, then the success will likely happen. Okay. However, if they view, okay, their company as a family society machine, then success will most likely to happen. Okay? In decision support systems, it's not going to be successful if they view their company as a war journey. But if they view their system or their company as a family society organism, then their decision support system will definitely succeed. So it's the same with the other types of information systems, such as expert system, cooperative systems, competitive systems. And you can see from the less successful metaphors that the company that are typically pictured out, such as jungle or zoo, something like connected to animals, for example, they are likely to succeed. However, if the family, or if the description of the organization or company is more like of a family, okay, like of a machine, a game organism machine, okay, a journey game organism and a war game organism, okay, they are definitely most likely to succeed. All right, so that's the metaphor, and it contributes to the success or failure of any information system. Now, security of computer facilities, as well as the stored data and information that are generated, is part of a successful conversion. So if we recognize the need for security, it's only natural, because nowadays security should be a responsibility, especially of those who come in contact with the system, and it's only as good as the most lax behavior or policy in the organization. So basically, in terms of security concerns, it has three interrelated aspects: the physical security, the logical security, and the behavioral security. And all these three must work together if the quality of security is to remain high. For example, in terms of this security, okay, so physical security refers to securing the computer facilities, no? Like for example, it's equipments, software through physical means. Okay, so it can include controlling access to the computer room by means of machine readable badges, biometric systems, or human sign in sign out system, as well as using closed circuit television cameras or CCTVs to monitor the computer areas, as well as those that are inside the facilities of the information technology infrastructure. Okay? The logical security refers to the logical controls in the software itself. So basically, the logical controls familiar to most users are passwords or authorization codes of some sort. Okay? And then when they are used, they permit the user with the correct password to enter the system of a particular part of the database. For the behavioral security, okay, of the organization, these are the things, okay, that are implicit, okay, and basically they are also critical to the success of security efforts, because behavioral security is about building and enforcing the procedures to prevent the misuse of computer hardware and software. So we can also make use of special security considerations, especially for e-commerce, because it's a well-known that intruders nowadays can violate the integrity of any computer system. And as an analyst, you need to take a series of precautions to protect the computer network from both the internal and external web security attacks. So the following are examples of actions and as well as products that can help us. So we can install virus protection software, email filtering products, URL filtering products, firewalls, gateways, virtual private networks or VPNs, and then intrusion detection products, okay, and then vulnerability management products, so those that assess potential risks in a system and discover and report vulnerabilities. We can also use secured shell or security technology such as secure socket layering or SSL, and this is used for authentication. We can also use encryption technologies, okay, such as the secure electronic translation or the SET. Finally, we can use public key infrastructure or PKI and digital certificates which can be obtained from a company such as VeriSign, wherein the use of these digital certificates can ensure that the reported sender of the message is really the company that sent the message. Okay? For privacy considerations, okay, we can also start with a corporate policy on privacy, okay, because the other side of security is privacy. And to make our website more secure, we need to ask the use of customer, or we need to ask the user or customer to give up some privacy. Okay? So as a web designer, you need to recognize that the company for which you design exercise a great deal of power over the data its customers are providing. So the same tenets of ethical and legal behavior apply to website design. As to the design of any traditional application that accepts personal data from the customers. Okay, so the web, however, allows the data to be collected faster and allows different data to be collected. Okay? In general, information technology makes it possible to store more data in data warehouses and process data and distribute the data more widely. So every company for which you design e-commerce application should adopt a privacy policy. Okay? And these policies, here are some guidelines for adopting privacy policy. For example, we can start with corporate policy on privacy. So we can make sure it is prominently displayed on the website so that all the customers can access the policy whenever they complete a transaction. So that's a corporate policy on privacy. So sometimes we see those information in some commercial sites wherein the information that we have given to them are kept in confidentiality or in private. Okay? Number 2, only ask for information required to complete the transaction. So for example, is it necessary to the transaction to ask person's age or gender? So definitely not. Okay? So we should only ask for information that the application requires to complete the transaction at hand. Okay? Number 3, make it optional for customers to fill out personal information on the website, because some customers, they don't mind receiving targeted messages. but you should always give the customers an opportunity to maintain the confidentiality of their personal data by not responding. Alright? You can also use sources that allow you to obtain anonymous information about classes of customers. So there are companies that offer audience profiling technology and technology solutions for management of advertisements, their targeting and their delivery. So they do so by maintaining a dynamic database of consumer profiles without linking them to individuals, by respecting customers' rights to privacy. Finally, we could be ethical. No? We can avoid the latest cheap trick that permits your client to gather information about the customer in highly suspect ways. So tricks such as screen scraping, capturing remotely what is on customer screen, and email cookie grabbing are clear violations of privacy, and it should be it may prove to be illegal as well. Okay, so we have to be cautious of those things. Now, no matter how diligently you and your organizational colleagues work to ensure the security and stability of the systems, all employees and systems are vulnerable to some kind of natural or, let's say, human-made disaster, no? And it threatens the security as well as the very functioning of the business. Alright? And when that happens, okay, which is very common, no? Disasters are very common, such as, for example, power outages. They usually happen. So basically, we can assess the probability of some disasters that are happening or that can happen, such as, for example, earthquakes, hurricanes, etc. However, many disasters are unexpected in their timing or their severity, so perhaps even causing the life of someone. Okay, so it creates chaos for people and the organization itself. Okay, so the fields of disaster preparedness and disaster recovery are interdependent, and they build on each other. So disaster preparedness includes what a company should do if it encounters a crisis. Okay? So the field of disaster recovery is focused on how a business can continue in the aftermath of a disaster and how it can restore essential systems in the IT infrastructure. So this section will focus on disaster recovery as it relates to information system. Okay? So as you will see, there are certain conventional wisdom which provides elements to consider during and after a disaster. Okay? And this involves information system. And it relates specifically to the planning required of the systems analyst. First thing to do is to identify the teams responsible for managing a crisis. Alright? Number 2, eliminate single points of failure. Okay? So basically, the disaster preparedness plan should identify who, in the event of disaster, is responsible for making several pivotal decisions. So these include decisions about whether business operations will continue, okay, how to support communications, for example, through computers, through voice, or where people will be sent if the business is uninhabitable, for example, okay, where the personnel will go in an emergency. Okay, so basically those are the things that we need to get used or to be prepared of. Okay, next is to determine data replication technologies that match the organization's timetable. So basically, redundancy of data provides a key or provides the key for eliminating single points of failure for servers running web applications. And as an analyst, you can be especially helpful in setting up this type of backup and redundancy. Okay? Some business are moving, for example, to storage area networks or SANs. So typically, they want to get away from some of the unreliability of those that are associated with physical tape backups and storage. Okay? Also, we should create detailed relocations and transportation plans. So basically, that's very easy to understand, right? What else? We could also provide recovery solutions that include an off-site location, right? So, for example, the company or the organization should develop and distribute a one-page memo that contains evacuation routes and employee assembly points. And this should be distributed to everyone in the organization. Okay? So finally, we need to ensure the physical and psychological well-being of the employees and as well as the others. Okay? This is used for disaster recovery planning. Whenever a disaster happens or occur, even in our information systems. Now, throughout the system's development life cycle, the analyst, the management, and the users have been evaluating the evolving information systems and networks to give feedback for their eventual improvement. And evaluation is also called for following system implementation. And in recognition that the ongoing evaluation of information systems and networks is important, many evaluation techniques have been devised. And these techniques include cost-benefit analysis. No? We already discussed it in chapter 3. And then these are models. We also have techniques such as the models that attempt to estimate the value of a decision based on the effects of revised information using information theory simulation, or we call it sometimes Bayesian statistics. We can also understand about another technique called user involvement evaluations that emphasize implementation problems and user involvement. And finally, we can understand the techniques such as the information system utility approach that examine the properties of the information. So basically, each type of evaluation serves a different purpose and has inherent drawbacks. For example, cost-benefit analysis may be difficult to apply because information systems provide information about objectives for the first time, making it possible to compare performance before and after implementation of the system or distributed network. Now, the revised decision evaluation approach presents difficulty because all the variables involved with the design, development, and implementation of the information system cannot be calculated or quantified. So the user involvement approach, it may yield some insights for some new projects by providing a checklist of potentially dysfunctional behavior by various organizational members, but it also stresses implementation over other aspects of information system designs. Finally, the information system utility approach can be more comprehensive than the others, and it's expanded and systematically applied. All right? So as we have said, the information system utility approach can be a comprehensive and a fruitful technique for measuring the success of a developed system. And it can also serve as a guide in the development of any future projects the analyst might undertake. And utilities of information include possession, form, place, time. And to evaluate the information system comprehensively, these utilities must be expanded to include actualization utility and goal utility. Alright? So, the utilities can be seen to address adequately the questions of who. So, definitely that it's referring to the possession. And what form, okay? Where, so that is the place. And when, so the time. And then the actualization explains the how. And why is the goal. So an example of this, okay? So we can see some example. Okay, the examples are written here in the information system utility approach. For example, the possession utility can answer the question of who should receive the output, while the goal utility answers the why of information system by asking whether the output has value in helping the organization achieve its objectives. Okay? The form utility answers the question of what kind of output is distributed to the decision maker, while the time utility answers the question of when the information is delivered. The actualization involves how the information is introduced and used by the decision maker. Okay? Now, finally, I think this is the last topic for this chapter. So, it's about website evaluation. So, evaluating website is an important part of any successful implementation effort. An analyst can use the information system utility approach. So, we describe the different approach so that we can assess the aesthetic qualities. We can also assess the content and the delivery of the site. And as an analyst or a webmaster, we should go one step further and analyze web traffic. Okay? For example, a visitor to your website can generate a large amount of useful information for you to analyze. Okay? So this information can be gathered automatically by capturing information about the source, including the previous, for example, website the user visited and the keywords used to find the site. So the information can be obtained through using cookies. Okay, so we can know how often the website is visited. We can learn details about specific pages on the site, and we can find out more about the website's visitors. Okay, so definitely these are all the things that we can evaluate. Okay, we can also gain valuable information using different services. No, we can discover if the visitor can properly fill out the forms that we designed. We can find out who is referring the website. Okay, and then we can determine what the browser's visitors are using, and we can find out, okay, if the client website visitors are interested in advertising. All right. Okay, finally, we have the following summary we discussed with this chapter. The first of all, we discussed the total quality management. Okay, we're in designing systems and software with a top-down or modular approach. We emphasize in designing and documenting systems and software using systematic methods. And then we discussed that testing systems and software so that they can be easily maintained and audited. We also discuss about Six Sigma. No? Six Sigma is focused on defining the problem, observing the problem, analyzing the causes, act on the causes, study the results, standardize the changes, and draw conclusions. We also discuss the definition of structure charts, the procedure manuals, and the folklore. And then we describe the testing, and then system maintenance, and then auditing, and then the implementation, especially in the side of distributed systems such as the client-server model. And then we discuss about training users and personnel, and the conversion of the old system to the new system. So we have guides like the direct changeover, parallel changeover, phase conversion, gradual conversion, and the modular prototype. And then we discuss the security. And there are 3 types of security: the physical, logical, and behavioral. And then we discuss about the different organizational metaphors. Finally, we discuss about the evaluations. Okay, so I think that's gonna be it. So I would like to thank everyone for participating and for your kind attention for this particular chapter. Thank you very much, everyone.